Start the recording. So, this is week 7. Okay. So the week seven actually mostly deal with the compensator and the controller part. Okay. So you have gone through all the lectures, I think. Okay. But still we have discussed the overview and then we solve some question which can easy for you to solve the assignment questions. So let me give a brief overview of what do you mean by controllers. Okay. Then I will solve some question on that. So controllers, so you know that suppose let's say this is a transfer function, okay? This is a control loop and this is called your system, okay? So in any system, if something will happen, let's some disturbance will come, some noise will come, then but I want a desired output at the okay, but to get the desired output, I have to set a reference input. So this is my reference input, okay? Now I have to pass this output to a feedback loop which is normally is gain is h of s, okay? Then this gain will go to a summing block, okay, where this reference input and this sensing output is compared and it will generate an error signal e of s, okay? So whatever, let's say in time domain it is e of t and this is in time domain, this is h of t. Now after this error we have to be eliminated, this error we have to minimize such that the steady state part, it has to be constant. It means in the steady state, whenever you achieve the steady state, whatever the error is there, the steady state error, that has to be reduced to zero or it will be very minimum value, okay? So what to do, we have to pass through a controller here, okay? So generally this controller transfer function is generally represented by something, well, let's say theta, okay, theta of t, and let's say this let's say system, let's say I'm writing it controller for you, and its output is represented by theta of t, okay? So now we have adding this controller in cascade, okay? So in control system, this controller can be in anywhere, it can be a cascade connection, it can be in parallel connections, but whatever in your codes, whatever in the week 7 it taught, this controller can be added in a series or in cascade format. So this controller, we know that this is a three type controller, okay? So first of all is proportional controller, okay, which is represented by its gain kp. Then an integral controller, which is gain is ki, and a derivative control, which is represented by its gain kd, okay? So combination also possible. Proportional plus integral we called a pi controller. Similarly, proportional plus derivative we called a pd controller, and combination of all the three is called a pid controller. So every controller has its own functions. Why you use a PED controller, why you use a PI controller, and where you use a PID controller, that depends on a system according to your system requirement. So just me give you an overview. Suppose I need a PD controller. So why we require a PD controller? So generally this PD controller, it increases the system bandwidth. Can you explain me? I mean, anybody can tell me that how it increases the system bandwidth? Suppose I am saying that it increases my system bandwidth. Let me give you an example. Okay. Let's say the system is given to you 10 divided by s plus 5. So this is a system. This is g of s. Okay. Here. This g of s is given 10 divided by s plus 5. If you draw the Bode plot of the system, then at corner frequency this 5, its gain is 0 and then suddenly it has a slope of minus 20 decibel by decade. So it is reduced. So at this corner frequency the slope changes. This is the transfer function of this function. Now if I add a derivative controller, derivative complements proportional plus derivative controller, if I add a PD controller, Generally, PD controller is nothing but addition of a 0 into the system. Let me add a 0 at some value s plus 2 divided by s plus 5. So I have added a 0 at 2 point. Now if you draw the same function, now it's Bode plot. There are two corner frequency. One is 2, another is 5. Now if you draw the transfer function, means Bode plot of this transfer function, now this is the combination of GC and GS. Okay, GCS into G of S. So this is the overall planned transfer function now. Initially it is only G of S. Now I'm adding the controller here. So in series, so this is a cascade fashion. So now if you draw the Bode plot, so now the Bode plot will be like this from 0 to 2 is constant. Then I'm adding a 0 at 2. So my slope will be increased from 2 to 5 plus 20 decibel per decade. Then again at 5, this plus 20 becomes 0 because I'm adding a pole. So this is the, now you can see. So now you can see previous case, the system is now, if you see the system gain is decreases and somewhere it will be 0. Okay, if you go extend this line up to infinity, then one person can say that in between 10 or 15 this gain will be approaches to 0. If we see the bandwidth in frequency domain, this is log omega, this x-axis is log omega. So now if we see the bandwidth, this bandwidth is only narrow part. Now if you see by adding a 0 into the system, now the bandwidth is increases up to infinity. This is constant up to infinity. See the bandwidth from 0 to infinity. So the bandwidth is increases. So I can say that whenever you are adding a PD controller, the system bandwidth is increases. Just remember this point. If the system bandwidth is increases, then what will happen? You know that your rise time is inversely proportional to your bandwidth. If the system bandwidth is increases, then definitely the rise time will decreases. If the rise time will decreases, time and speed are inversely proportional. If time is decreases, then speed has to be increases. So means the system performance increases. So you can say that I can reach my steady state at faster rate. It means the transient performance is improved by adding a PD controller. Till now everyone clear? Means whatever I told you about PD controller. Any doubt?
Clear, sir, clear.
Okay, so so whenever you require a system where you require a transient performance has to be steep, means critical, means you have to increase your transient performance, then you have to add a PD controller. Okay, but where you add a PI controller, simply same thing. If you add a PI controller, let me give this PD controller little bit another overview. Generally this PD controller, let me go here. This PD controller whole transfer function, generally this GCS, whatever the controller is there, that is generally represented by KP into 1 plus KDS. Okay, so this is KP into 1 plus TDS. Okay, okay, this TD is nothing but your KD by KP. Okay, this is called your derivative rate. Okay, derivative rate. So generally it is also called set rate. Okay, set rate. So what you do whenever you saw a question, you have to either represent your GCS either in this format, in time constant format. Always represent your function in time constant format. So generally what is this? This, if you solve this putting, then GCS nothing but KP plus this KP cancel. So it will be KD times of S. We know that this is a P controller. This is a derivative controller. Whenever this addition is called a PD controller. So just I take the KP common and represent KD by KP as TD, because why? To represent in time constant format. That's why nothing is there. So similarly, when you come to your PI controller, so PI controller is generally represented by your KP plus how much? 1 by TIS. Okay, what is your TI? The TI is called your derivative rate or reset rate. is इसको reset rate भी कहते हैं. तो TI is nothing but how much? In time constant form, KP by KI you have to represent. Okay, so this is your TI. This is called your reset time or derivative, sorry, derivative, sorry, it is called integral, sorry, integral time or reset time. So what is happening, you can see here, suppose if you add a, if you saw this, you can see that this is normally kp plus ki by s, this is represented by this. So if I take simplifies, this is kps plus ki divided by s. So now this is your gcs. Suppose your g of s is given, suppose 10 divided by s plus 2, and you are adding this gcs here. So now your transfer function becomes how much? G of s into gc of s. So it will be 10 divided by s plus 2, initial it is there, and you are adding kis plus ki divided by s. So what is happening, you just see, simply you can observe that you are adding one pole at origin. Whenever you are adding one pole at origin, then type of the system increases. Okay, so type is nothing but the number of poles at origin. Okay, so whenever you were previously, this is a type 0 system. Okay, there is no pole and 0 at origin, but now whenever you're adding an integral controller, your type is increases to 1, so type of the system increases to 1. Okay, so whenever any system, I told you, in whenever we have read about steady state error, just recall that there are two things. One is type, another is your input. When is type is equal to your input, then you are getting some steady state error. When type is greater than your input, your steady state error equal to 0. When type is less than input, your steady state error equal to infinity. So this thing already you have covered in our steady state part. Okay, so whenever your type of the system increases, remember that the steady state error value is going to 0. It means you are adding a pi controller that makes the system error to reduce. Okay, system error reduces, and that going approximately around 0 if your input is like that. If your input is less than type, then your steady state error becomes 0. So remember this thing, that whenever you're adding an integral controller, then it improves the steady state performance. Then the steady state error is reduces to 0. Then what will happen, your system may approaches to the stability faster. Okay, then means your accuracy of the system, when error is reduced, what is the meaning of that? The meaning of that is that the accuracy is increased. So remember that integral controller improves the steady state performance, and your derivative controller improves the transient performance. So whenever in any system you require both transient as well as steady state, then you are using a PID controller. This is the concept of the controllers. Okay, but how we are solving the questions, how we are going to solve the question, let me quickly introduce one or two questions for you. So now you can solve this question. What is this is a derivative controller. What is its function? He is asking mainly the what is the function. Which one is the answer? Improve the steady state error, derivative controller. No, it is not. It is only dealing with the transient part. Okay? Transient part means what? Transient part means, suppose this is my, suppose a step response I'm adding. Suppose one response is coming like this. Okay. So this is second order response. Now transient response means whenever you're adding a derivative controller, what is happening? It reaches to the steady state faster. Okay. Transient performance is increases means what will happen? It reduces the overshoot or it increases the overshoot? Anybody?
Reduces the overshoot, sir.
Why?
It will reach uh, transient. That is, transient is minimized means
Yeah, transient means transient performance is reduced. Okay,
it's
so it
so
means definitely it reduces its peak
overshoot.
value. Okay,
Yes,
this
sir.
overshoot value is reduced.
Reduces.
So it reduces the overshoot. It increases the overshoot is wrong. Degrade the stability of the system. Stability of the system can't say by only derivative controller. So you can't say about stability. Stability is determined by either combination of PPI or PPD. So whenever suppose another word you can say that, suppose your this value is reduced, suppose your peak overshoot is reduced. If peak overshoot is reduced, definitely your stability will be improved. cannot be degrade. Okay, in one sense you can say. So this is also not correct. So this is a function of derivative control. Similarly, you can, if suppose one question will come from integral controller, then you have to think about the steady state part rather than the transient part. Okay, so next go to the second question. This is the question. It is given that this is, I am just drawing the transfer function for you. This will be easy for you to understand. This is g of s. This is a plant. Okay. Now this plant is having some input and output. Okay. So generally, let's say this output is y of s, and this y of s is having a feedback h of s, and you are going to a summing block where you defined your desired value, the reference input. Your output has to be tracked to this reference input and to generate some error E of S. You know this circuit very well in steady state part. But what is happening now? This error we have to be eliminated. Who will eliminate this error? This error cannot be eliminated by this plant, okay? Because the plant cannot, whatever the error is coming, the plant cannot be nullified. So we have to, in between that, we have to introduce some, let's say, controller, okay? So I'm introducing a controller which is transfer function is GCS, which is having input whatever the error signal is coming. That error is coming here E of S. Now output of this, let's say theta of S. Okay, this is your controller. Now you can understand. See this in time domain it is represented by theta CT. Okay, this value is combination of 20 into E of t, whatever the signal in time domain is E of t. Okay, so it means you can see that this is a kp term. Okay, some constant into error. Okay, similarly this is called d by dt term, derivative term. So derivative term, if you go to the what I told in the earlier slide, if you see this derivative control represented by kp plus 1 plus tds. Okay, so kp plus 1 plus tds, you can see if you take that this the difference in term, let's say derivative term. So this is kp term, 20 is kp, so kp plus td. If you differentiate this Laplace transformation will be s times of e of s. So you can, by seeing this question, you can observe that this is a combination of kp plus kds. Okay, this derivative controller plus proportional controller. And here GCS is given 40 divided by 10s square plus 80s plus 800. So he's asking us to find out the derivative time. Derivative time is dd. Okay, required to make the closed loop damping ratio unity. Okay, damping ratio, whatever zeta is called, that is 1 is given to you. Okay, so what is this TD value? How to solve this question? How will you approach this question? So first of all, what you do, this is GCS is given. First of all, you have to find out the transfer function of this controller. Controller transfer function is nothing but theta of s divided by E of s. Okay, theta of s, E of s is nothing but your GCS. Okay, so find out this GCS from this equation. Okay, if I take the Laplace transformation, I will write this equation in the next slide. Okay, let me write somewhere. Bring next slide here. Now, now I can see GCS and GC, G of S and GCS you multiply first. Okay, first before that you have to find out what is GC of S. Okay, so GC of S is nothing but theta of S divided by E of S. So first of all you have to find out what is theta of S, because theta CT is given. Take the Laplace transformation, then you find out theta S. So theta S will be 20 times of E of S plus this 20 will be multiplied 20 times of TD into S of E of S. Okay. Now theta of S by E of S you find out, which is nothing but your GC of S, which is 20 plus 20 STD. Okay. This is the transfer function GCS. Now what you do, g of s into gc of s, first to find out multiplication of this. What is gc of s? G of s is given 40 divided by 10s square plus 80s plus 100. So write down 40 divided by 10s square plus 80s plus 800 into gc of s is 20 plus 20 std. Okay. So now this is your overall transfer function. After the overall transfer function, go back to the question and read the question carefully. Is seeing that to make the closed loop, okay, to first of find out the closed loop damping ratio unity. So for this open loop transfer function, the unity feedback system is given because it in the question it is mentioned a unity feedback system. So assume that a unity feedback system and find out the closed loop transfer function. So how will find out the closed loop transfer function? I told you the shortcut 40 into, write down the numerator 20 plus 20 STT, whatever the denominator you can write down that 10s square plus 80s plus 800 plus whatever this numerator just add in the denominator. So 40, this will be 800 plus 800 STD. Okay, now just simplify it. So it will be 40 into 20 plus 20 plus 20 STD divided by, just simplify it, the second order equation. So 10s square plus s you take common, you take s common, this will be 80 plus 800 td into s plus 800 plus 800 is 1600. Okay, this is a closed loop transfer function. Okay, after everyone is clear.
Yes, sir.
Okay, now so what is saying then the question? Then the question is saying that the damping ratio, closed loop damping ratio is unity. So you know that this is second order equation. Okay, this is second order equation. In the second order equation, you have to compare the standard second order equation for a unity feedback system. So what is that? Omega n square divided by s square plus 2 zeta omega n s plus omega n square. This is the standard second order equation. Now you compare. So if you compare this value, so first can anybody tell me what is omega n square? If you compare what is omega n square,
Thus, first of all, we have to divide by with denominator with 10, sir.
right?
Then
You have
only
to
we can.
first divide 10 into, because this is standard equation. So first to divide by 10. If you divide by 10, this will be s square, this will be 8, this will be 80, this will be 160, right?
Yes, sir.
Now your omega n square equal to 160, right? Now you find out omega n. So omega n is root over of 160. What is the root over of 160? 12.65. So omega n is 12.65. Okay. Then what you do, you compare 2 zeta omega n equal to this value. This value is nothing but 2 zeta omega n. So I'm writing here. So 2 zeta omega n, this value is equal to 8 plus 8, 8 plus 80 td. Okay, you know zeta is 1 because in the question it is asking us that damping ratio is 1. So 2 into 1 into omega n is 12.65. This has to be equal to 8 plus 80 td. So in this equation only td is unknown. To find out td, what is the value of td? Okay, whatever the td you will get, that is your answer. So in this question the trick is that you always, before it is 10 square is there now, you have to divide by 10, because people will do mistake that they will directly 10 omega n square equal to 1600, omega n is equal to 4, okay, 40. So this is wrong. Okay, so you have to, whenever you are equating the standard equation, you see the standard equation coefficient is 1, so you first make the coefficient here 10 equal to 1. Okay, then whatever your omega n is coming, that is 160, and you solve this question to find out the derivative time control. Okay, So like this type of question will be asked in the examination. Okay, so
Okay, sir.
next, going to the next question. Yeah, this is a tricky question, but it's a simple question. So, a unity feedback flows. First of all, every line you have to read. First of all, if I read this up to this to this, three information is given. First of all, this is a unity feedback system. Okay. Secondly, he's giving that a closed loop system. Okay. For a closed loop system, this is the transfer function is given. So we first do whenever you see a controller question, always do like that. G of S and this is your GCS. Okay. Two block you have to make and this is your E of S and this is your output Y of S. You have to do that first. Then you see G of S is given. Okay. So 1 by S square plus 2S plus 1 is given. Okay, this value is given to you. Now he is asking that the controller you choose. These are the controller. Four controller is given in the question. So one controller you choose and fit in this box such that the transfer function of the controller gives minimum steady state error. Minimum steady state error. So steady state error minimum. So what you do such that the steady state error will be minimum. So how you choose this question? How you solve this question? First of all, whenever some question will come into steady state error, na, you first check the input and type. Okay. So now always make this block type and input. You know that when type is equal, both are equal. Okay, I'm writing the equal sign. Then some steady state error will become for step input that should be a divided by 1 plus kp, right? If it is a ramp input, then it should be a divided by kv. If it is a parabolic input, then a divided by ka. When you type equal to input, then some steady state value will come and that steady state depends upon the input which one you choose. But here in this question, the unit step function is given. So you know that unit step function. So this one is not there. So only the steady state value will be a divided by 1 plus kp when type equal to input. Okay. Now you come and check everywhere. So here in GCS the type equal to 0. This is type 0. Now go to, you find out, then come to here. If I put s plus 1 divided by s plus 2 here, then its type also 0. So both type 0 and type 0, when they are cascade, they will be added off. So type 0 plus type 0 is type 0. So now type 0, but your input, your step input. Input step means इसका value 0 ही होता है. So in that case, some steady state error will come. Okay, and the steady state error will be a divided by 1 plus kp. A is 1 here because a unit step input is given. Suppose 5 u of t is given, then this a value should be 5. Okay, so it is normal unit steps, that's why a equal to 1. So now your formula will becomes 1 divided by 1 plus kp. And what is kp value? Kp value is nothing but your dc gain. Remember, kp is always your dc gain whenever you are finding out by using this formula. Okay, so kp is nothing but limit s tends to 0 gc g of s into gc of s. Okay, like that. Okay, so what is that? This is called your dc gain. Dc gain means we are putting omega equal to 0 in the transfer function, that is called dc gain. Okay, so now you put omega equal to 0 or s equal to 0 in the transfer function. If I put s equal to 0, then my gcs will be half. If I put s equal to 0 in my g of s, then it will be 1. So 1 by 2 is coming. So now if you put kp equal to 1 by 2, 1 divided by 1 plus 0 0.5, 1 divided by 1.5. 1.5 is how much? 3 by 2. So it will be 2 by 3. So for the first case, the steady state error will be 2 by 3. Are you following me? How I find out the steady state error for the first one?
Sir, please explain this, sir. Type input from that.
Uh, sir, I had already explained this in the steady state
Yes,
error
okay.
part.
Yeah, stage sir. In earlier chapters, you explained, sir. Okay.
Yeah. So now what I told you, so you just see type and input. Okay.
Okay, sir.
So
Okay.
input means what? There are three types of input in your control system. One is
Yes,
your
sir.
step input, one is your RAM input, another is your parabolic input.
Parabolic series.
Okay, so whenever you step is u of t, u of t means it's a coefficient t to the power 0 हो, right sir? Right, t to the power 0 is 1.
Yes, sir.
So
Yes, sir.
whatever the t to the power, the power you have written in input. Okay, so for whenever unit step is coming, you see the t ka power 0 hai, so that's why I'm writing 0 here in input. But in ramp this will be t u of t, right sir?
Okay, sir. Right.
So power is 1, that's why I'm writing input 1. For parabolic input this will be t square by 2 u of t, right? So t ka power 2 hai, so I'm writing 2. These are my input. Now type means what? Number of poles at origin. Now you see type 0 means no poles and zeros at origin. So in this case your type equal to input. When type equal to input in 0 case, okay, so in this case some steady state error will become because these two values are equal for a unit step input. This 0 means for a unit step input. So in that case, you know that your steady state error value is nothing but 1a divided by 1 plus kp. Kp is your positional error constant, right sir?
Yes, sir. Yes, sir.
So now if type is 1, if type is 1 means a transfer function will be like this. So here power is 1. If it is 1, both are equal. It means for this system, in question it is ramp input is given. Then these two are equal. In that case, some steady state error will come and that should be 1 by kb. Kb is nothing but velocity error constant. Similarly, if you take a parabolic input, suppose in the question it is given t square u of t and type is given 1 divided by s square s plus 1. Now you see these two and these two are equal. If these two are equal, then at that condition there is some error will come steady state that is equal to 1 by k acceleration error constant. If it will be not the case like that, suppose you know that when these two values are matches means type equal to input, in that case there will be some steady state error will be occur. And in other case, if type is greater than input, then the steady state error equal to 0. If type is less than input, then steady state error equal to infinity. We have solved many questions on that. Okay, so but coming to this question, okay, you come to this question, you clarify. So now I'm just removing all this. If in this question you just make a block like that, okay, first make a block and write down here type and input. Now you see what is the type of the system. Type of the system depends upon product of GCS into G of S. But what is the type of G of S? 1 divided by S square plus 2S1. So no poles at origin. No poles at origin means for GC of S, always my type equal to 0. Right? Now if I multiply GCS, there are 4 values of GCS is given. I don't know which one is the correct answer. Let me choose the first option A. If I choose option A, इसका भी type equal to 0 है. There is no poles at origin. So type 0 is going to be type 0. So addition of type 0 is 0. It means here in this case, if I choose the option A, then my type will be 0. And see the input. Input in the question is given unit step input. You know that for unit step input, it is t to the power 0. So this will be 0. So when these two are matching, it means some error will come. And in unit step input, this will be 1 divided by 1 plus kp. Okay, you have to find out this kp value to find out the steady state error. So kp is nothing but limit s tends to 0 g of s into gc of s. It means multiply these two transfer function and put s equal to 0. If I put s equal to 0 on my gcs, I will get 1 because this is 0, this is 0, so 1. And if I put s equal to 0 in gc of s, this will be 1 by 2, right sir? So इसका
Yes.
इसका 1 by 2 आया और इसका जो क्वेश्चन दिया हुआ है इसका ऑलवेज 1 है इज इक्वल टू 0. So 1 by 2, so total is 1 by 2. So put kp equal to 1 by 2. I'm just writing out here. So the steady state error here is 1 divided by 1 plus kp is 1 by 2. So 1.5, this will 1. So 1.5, 1 divided by 1.5 is 2 by 3. Right, sir?
Yes, sir. Yes, sir.
Now, but in the question it is giving that which GCFS will choose so that this error, whatever you are finding out, that will be minimum. For the first case, you find say 2 by 3, but I don't know if another person will choose option B. Let's see option B. If you choose option B, this is type is 0 again. This type is 0, that type is 0. Again, a unit step function. So now, what is the DC gain of this? This is 2 and this is 1. So this will be 2. So find out the steady state error. 1 divided by 1 plus Kp. Kp is 2. So this will be 1 by 3. Are you following me?
Yes, sir. Yes, sir.
Now, if you, another person will choose option C, then it is also say type 0 and GC also type 0. Means some steady state error will come and find out Kp value. Put S equal to 0. If you put S equal to 0, then you will get 4 by 6 here. And for our transfer function, the Kp is always 1. Okay. So multiply 1, so it will be 2 by 3. If then again you put the formula, find out steady state error. So 1 divided by 1 plus 2 by 3. Some value will come. Now, if you go to option D, sir, if you go to option D, then then if you multiply this GCS into GFS, you will get a pole at origin, right, sir? Because one pole is already in
Yes,
the
sir. Yes,
origin.
sir. Yes, sir.
So
Yes, sir.
origin में आपको जो pole मिल गया sir, whenever one pole you will get at the origin, your type of the system is how much now, sir?
One, sir. One.
So now type is one, type is one, but what is your input? Input is 0 because step input, sir, right? Question given step input, right?
Okay, sir. Okay.
So whenever type is greater than input, then what is the steady state error, sir? Infinity, right? Sorry, 0, right? When type is greater than inputs, error is 0, right, sir?
Yes, sir. Yes.
So for the last case, the steady state error equal to 0. So now you see which option will be fit. Minimum steady state error will be the last case, right, sir?
Yes, sir. D. D. Yes, sir.
So if you look at the question without solving, sir, you can say that the answer is D. Because if you know the concept of type is greater than input or type is less than input. In all the cases you see your in all these cases this is type 0, this is type 0, this is type 0. As soon as you see this is type 1 and your input is given a step input, you see that your type is greater than input. So your steady state error equal to 0. It means now, out of all the cases, the option D will be gives me 0, 0 steady state error. That is the minimum value. Right, sir? Are you following me?
Yes, sir. Yes, sir. Father.
Okay. So in controller, mainly this type of question they will ask, okay? Yeah, they will introduce one proportional controller or proportional plus derivative controller, proportional plus integrative controller, and they will ask related to find out the derivative time control, find out the reset time, find out the steady state error. Means this part is related to all the whatever you read till now in time domain, frequency domain, Bode plot, root locus. All the concept will be used here. The question can be anything. It is just an addition of another transfer function. Just now the transfer function becomes a multiplication of GCS and GFS. That's it. Nothing is there. So now you come to question number 3. Read the question and try to solve, because already this question I have solved. So G of S is given how much? 2 divided by S into S plus 3. Now a PI controller is given. So now your GCS is something Kp plus Ki by S. Okay. Because it is given in the question that Kp equal to 1, you put 1 here, and Ki का value आपको पता नहीं, Ki is greater than equal to 0 in a unity feedback system. Then what is the value of Ki that ensures zero steady state error for a step change in the reference input? So input is given as step input. Unity feedback system. What is the value of Ki? Ki should be greater than equal to 0 is given. So you have to choose which value of ki out of these four such that my steady state error equal to 0. Sir, are you following me?
Yes, sir. Yes, sir.
Now you see this question. Now, if you read the question, you can tell the answer without fraction of time. Just apply the concepts, type and input. So what is your input, sir? 0, right? Why? Because it is step input. Step input means t equal of t. T का power क्या है? 0 है. So that's why I've written input is 0. Are you getting my point, sir?
Yes, sir. Yes, yes.
Now come to type. Sir, he is asking us type, but you are adding an integral controller. Whatever the transfer function you see, g of s equal to 2 divided by s into s plus 3. Your GCS is how much? Your GCS is how much, sir? Your GCS is s plus ki by s. Now, your whole transfer function is how much? G of s into GCS. If you write down, then it will be 2 times of s plus ki divided by s square into s plus 3. Now tell me, sir, what is your type?
Two, sir. Two.
Type is 2. So type is greater than input or not, sir?
Yes, sir. Yes, yes.
It will be always type is greater than input. Then your steady state error will be what will happen in the steady state error? Is a type is greater than input means steady state error is always 0, right?
Yes, sir. Yes, yes.
In the question it is asking that 0 steady state error. But sir, in this question, whatever the value ki choose, whatever the value of ki, this a square terms will be independent of this ki, right? Ki is just a constant, sir, 5,
Yes,
3,
sir.
2,
Yes, sir.
whatever.
Yes. Yes,
But
sir.
your type is always greater than 2. Means type is greater than input. So steady state will be always 0. Means for all the values of ki, this steady state will be 0. Sir. Because your type is greater than input. That's it.
Okay,
Okay.
sir. Okay. Clear.
But
Clear. Clear.
if I change the question like this, how I change the question like this? Suppose in this question, if I not give no, instead of giving a step change, if I give a parabolic change, then what will happen? Your type is now equal to input, right, sir? Because for parabolic
Yes, yes.
input, this will be t square by 2 e of t, right? So t equal
Yes,
to
sir.
2 and your type is now 2. Type 2, input 2. It means the steady state error, I cannot say it is 0. There is some value of steady state error will be exist, right, sir?
Yes, sir. Yes, sir.
Let the steady state error is a function of 1 by kp. Because in this, if you solve, then only one unknown is there, this is ki. So let's this steady state error in terms of ki. Let's say, sir, I'm giving 5 divided by ki plus 3, right, sir?
Yes, sir. Yes.
Then in the question he is asking us that 0 steady state error. So you now put your steady state equal to 0 and find out ki value. For that particular value of ki, now your steady state error will be 0.
Okay, sir.
But as your type is greater than input, whatever the ki you choose, so now the answer will be like. You have to understand what I'm trying to say, right?
Okay, sir.
Hope you got my point. Come to the next question. Uh, okay, try to solve this question, sir. Question number 4. If a proportional controller GCS is KP is used, so this GCS is nothing but KP. Okay, find the value of controller gain KP. What is this value of KP such that the steady state error is 0.25. The steady state error is 0.25 for a ramp input. So first of all, same concept we apply, sir, here. Your type and input. Input is RAM means what value will write, sir, here?
One, sir. One. T to the
Right?
power zero.
T to the
T to
power
the power
1
one.
u of t. So
Yes,
1. Now you come to the type. Type, how will you get? First product of GCS into G of S. So GC of s is nothing but Kp, and this will be 4 times of s square plus 2s. So if you take 4Kp divided by s common, then this will be s plus 2. Now you see one pole is exist at origin. It means it is a type 1 system. So type equal to 1. Okay, sir?
Yes, sir.
Now you tell me when both are equal, then what is the steady state error value? What is the formula of steady state error? 1 divided by kV, right? Because it is a ramp sequence, right? So I'm trying to
Yes,
join.
sir.
Let me add. So it will be 1 by kV, right? So now, but in the question it is giving that the steady state error is 0.24, 0.25, write down 0.25, and what is 1 by kV. Okay, so tell me, sir, what is kV? KV is what? Limit
4, sir.
s
No.
tends to 0, no. KV
Okay,
is
sir.
velocity error constant, which is
Okay,
s
sir.
times of GCS into G of s. So in this transfer function, what is given? We just put s equal to 0 and multiply s. So it will be 4 Kp by 2. So 2 Kp. Kp is 2 Kp. So now 1 divided by 2 Kp. From here you find out Kp value. 2 Kp is equal to 1 divided by 1 by 4. So 2 Kp equal to 4. So Kp equal to. Okay, sir? Are you following? This is this is just formula, sir. Nothing is there. Because why actually in all the question you are seeing steady state error? Because sir, in controller part you are trying to eliminate the error. So in most of the question, whatever the question will come, the question is having the term steady state error always. If there is nothing related to bandwidth, rise time, in some question second order system, whenever you are adding a derivative control, it will increase the bandwidth, means it will decreases your rise time. So in that case, if this is a function of again rise time bandwidth, but most of the question will come to steady state error part, because by adding a controller you are eliminating the steady state error. That's why whatever in all the question you are seeing, all the question belongs to steady state error. So this is all. If you strong in steady state error, whatever I told we discuss in the lectures, then this controller is nothing but this is an easiest subject. Okay, so but designing a KI is an iterative process. Okay, so that required a steady state modeling. So that is a different. But here we are just trying to solve the questions. Maybe in some for art next after 1 or 2 week, whenever you go to modeling part, MATLAB function you will use to solve. You can see how the body plot will vary by adding a compensator controller. Then that thing you can see. But here actually the questions will be you can solve like this. So I'm going to the next question. Okay, same question I think. Okay, so what is the same question? Okay, GCS and this same transfer function is given, but the question is something different. If an integral controller ki by s is added in the forward part, then the steady state error to unity ramp input. Can you do that, sir? For the same question. Just time copy that. I paste here. Okay. Same transfer function, same block diagram, but the now question will be like this. Forget about the question number 4. This one you just forget. Now come to question number 5 for the same transfer function. This GCS is now Ki by S. The steady state error is 0 to a ramp input. No, he's asking us the steady state error. What is the value of steady state error? So first to write down ki by s into 4 divided by s into s plus 2. So it will be 4 times of ki divided by s square into s plus 2. Okay, so now you can see your type is how much? Type is 2. Type is 2, sir, right?
Yes, sir.
Type is 2. What is your input?
One, sir.
Then what is your answer? What is the steady state error, sir?
It's zero, sir. Zero.
Type is greater than input, right, sir? So steady state error is 0. If you find out also, na, sir, by using your formula, then you will get 0. Okay, so no need to find out. Next, for the same question, for the same block diagram, if I'm adding a question, if a 0 is added to g of s at s equal to minus 2 with gcs equal to 1. So here gcs equal to 1 is given, and in this plant one 0 is added, but that 0 at which point? S equal to minus 2. This means 0 is on the left hand side of the s plot. So now you can say your gc of s equal to 1. The question is given. Now my g of s previously it is how much? Previously is 4 divided by s square plus 2s. Now here I am adding a 0. 0 means you have to add a 0 on the numerator, at which point s equal to minus 2. It means you are adding a 0 like this. So your transfer function is now gc of s into g of s, which is nothing but multiplication of these two, is 4 into s plus 2 divided by s into s plus 2. Right, sir? S plus 2 s plus 2 get cancelled. So now your transfer function is only 4 by s. Now, he's asking us the velocity error constant. Sir, velocity error constant. Okay. Now, you just tell me, what is the type of the system? Sir, 4 by S. Type is
It's
1.
one, sir. One. One, sir. One.
Now, you tell me, in the question, he is asking us intentionally to find out the velocity error constant. Sir, velocity error constant, we are normally find out by input. Which input? Ramp input, right, sir?
Yes, sir. Yes, yes.
So if velocity error constant is given in the question, it means ramp input. If it is saying that positional error constant, it means step input. If it is saying that acceleration error constant, it means parabolic
Parabolic.
input. So ramp input means, for ramp input type is how much? Sorry, what is the order is for ramp input? What is the input value?
One,
1.
sir. One.
So type is 1, input is 1. So what is the steady state error, sir? 1 divided by kV, right?
Yes, sir. Yes, sir. Yes.
So steady state error in the question, the velocity error constant kV is how much? So now find out the steady state error. No, he's asking us the velocity error constant. No need to find out the steady state error. So velocity error constant is nothing but
Limit
limit s tends to 0, s into g of
G
s
of
into gcs.
G of S.
So 4 by s into s get cancelled. So only 4 is remaining. Limit s tends to 0, 4 is 4. So the answer is 4. So normally, sir, the question will be like this only. You can solve the questions. If you doubt, you can ask me. Now go to the next part. The next part is compensator. Okay. So control part will have solved some questions. Let's go to control. Then the interesting thing. So okay. Another same thing is that if 0 is added, another question is there. Just note down the question and tell me the answer. Then we will move to the. This is the last question. Another question is there. Okay. Lots of questions. Okay. Uh, First solve this question, then we'll go. We have time. If the 0 is added to the same transfer function, okay, same block diagram, GC of S, G of S is 4 divided by S square plus 2S. Okay, there get cascade. Now he's asking GCS is 1, so this value is 1. But if a 0 is added at S equal to 2, S equal to 2 means it is in the right hand side of the S plane. Okay, a 2 point here. Now your G of S is 4 divided by S square plus 2S. Now you are adding a 0 at S equal to 2, it means S minus 2 term. This is your G of S. Then he is asking us the closed loop system is stable or not. So GC of S is 1. Okay, so I am not here adding it. So total transfer function is this much. Total transfer function is 4 into S minus 2 divided by, this is the product of GC of S into G of S, which is 4 into S minus 2 divided by S into S plus 2. Okay. Now the closed loop system, he is asking us not the open loop transfer function. He is asking us the closed loop system whether it's stable or unstable. Open loop transfer function is unstable by default. Why? Because one G, no, open loop transfer function is stable because all the poles are in the left hand side. Okay, because stability does not affected by the 0 on the left, 0 on the right hand side. Okay, so now, but the closed loop system, find out the closed loop transfer function. Closed loop transfer function for a unity feedback system. So I told you how the shortcut. Whatever in the numerator, you just add in the denominator. So this will be S square plus 2S plus 4S minus 8, right? So it will be 4 into S minus 2 divided by S square plus 6S minus 8. So the characteristic equation which is in the denominator, S square plus 6S minus 8 equal to 0. Okay. Now from the characteristic equation you see that a second order system is there. I told you the shortcut. Whenever a second order system is there, a square, standard formula, a square plus bs plus c equal to 0, then the system will be stable when a greater than 0, b greater than 0, c greater than 0. Okay, if b equal to 0, then the system will be marginally stable. I told you this. Okay, otherwise what you can verify by using RS criterion. So this is up to second order and third order. I told you the shortcut. Okay, don't find out the RH criterion. So this is second order system where one coefficient is negative, C is less than 0. It means whenever one coefficient is less than 0, the system is unstable. Okay, so the system is unstable. Are you getting my point, sir?
Yes, sir. Yes.
So in this way you have to solve the questions. Now another question I think left. Question number 8. So okay. So consider the feedback system shown below. The process transfer function is marginally stable. Okay. So it is given that this transfer function is marginally stable. Okay, that is the first point. Next, you are introducing a controller which is a PD controller. So PD controller transfer function is given Kp plus KDS. Okay. Now he is asking us to find out the characteristic equation of the closed loop system. A simple question. Characteristic equation means what? GCS into G of S is 10 into Kp plus SKD divided by S square plus 10. So what is the characteristic equation? Just unity feedback system. So S square plus 10 plus add the numerator. Okay. 10 Kp plus 10 SKD equal to 0. So this is the characteristic equation. So it will be S square plus 10 SKD 10 common गया 1 plus kp. So answer D, option D will be correct. Are you getting my point, sir? It's just simple characteristic question. Find out the characteristic question, right?
Yes. Direct problem, sir.
This is a direct problem, sir. But is question number 9 is there, okay? And which is related to question number 8. The same transfer function 10 divided by a square plus 10. A proportional derivative controller is added. But what is saying? He's saying that let the time which is defined as some time. I told you this is the derivative time, which is nothing but kp by kd. Okay. He's saying that take this, okay, and let express the characteristic equation. Whatever the characteristic equation we get from the last, okay, that expression you have to express in Evans form. So Evans form is normally represented by like this. So this is the Evans form का ऐसे ही represent किया जाता है. So we have to represent the Evans form like this: 1 plus kd, some numerator and some denominator. So he's asking us to find out the numerator value and what is the denominator value in this format. Which format? 1 plus kd into numerator s by denominator s equal to 0. So what is the characteristic equation we got from the last? Just write down here s square plus 10 kd is 10 into kp plus 1. I'm just writing out the characteristic equation here. S square, characteristic equation equal to s square plus 10 kd s 10 kd s into 10 kp plus 1. 10 kp plus 1 equal to 0. So this is the characteristic equation. Now I will represent this characteristic equation in this format. Okay. This is also direct question. You just use this tau d is equal to kp by kd and find out the numerator and denominator. Okay. So I'm just writing out s square. So 10, because in this equation kd is there, right? So wherever kp is there, you replace with kd. So kd is there, I keep it 10. Kp I can replace kd into tau d plus 1 equal to 0. Now I just want 1 plus something by something. So what you can do, just simplify this: s square plus 10. If I take kd common, because this is kd is coming here, then it will be 10 tau d plus 10s equal to 0. Okay. Then this s square plus 10, I will just divide everywhere. So if I divide, I will take like this: 1 plus kd 10 tau d plus 10s divided by s square plus 10, that equal to 0. Okay. This is my characteristic equation. So now you can see this characteristic equation is now in this form. Okay. So 1 plus kd times of some numerator and some denominator. So now you choose which one is ns, which one is your ds. So s square plus 10 is your ds and 10 kd plus 10s. 10 kd plus 10. So option C will be correct.
Yes, sir. Yes.
Okay. So now this is a question why I take, because actually some Evans formula, Evans, how you represent in Evans way. So these are all previous question from the NPK I just chosen. Now let me go to an advanced, that is the next part, that's compensator. Okay. So what do you mean by compensator? Why controller is over? Then why compensator came? Okay. So what compensators exactly do, that you need to understand now. Okay. So now there are two types of compensator. One is your lag compensator. You know that is a lead compensator. These are all the things in the lecture. Okay. Some part is there. I'll just solve few questions and I'll make you understand that what do you mean by lag and lead compensator basically. Okay. So now see, remember that lag and lead means suppose I'm applying an input here. Okay, let me applying a sinusoidal input in my input. Okay, now this is your plant. Okay, now you'll get some output. Let's say this output, okay, whatever the output is coming, this output is having a like this. It means you can see the phase is now, let me lead the phase. So now you can see your phase is now leading by this angle theta. Okay. So if you apply a sinusoidal input and to a plant and you will get some output, which phase, you have to check the phase which is having a leading with respect to the input, then that type of plant is called a lead compensator. Okay, this plant is now called a lead compensator. It means your phase is now lead by some angle. Similarly, for lag compensator, if you apply sinusoidal input and you are applying a compensator and you are getting some phase lag, okay, getting some phase lag like this theta, then that compensator is called a lag compensator. Generally, your lag compensator and lead compensator, can anybody tell me which one is which type of filter? It is a high frequency, high pass filter or low pass filter. Lag compensator is what? Low pass filter or a high pass filter? Similarly, lead compensator is what? High pass filter or low pass filter? Anyone? They are just doing filtering action. Nothing that. See, if you don't know, then what you do? First, try to understand that what is lag. Lag means what you lagging means your phase is getting lag. Okay. So whenever represent a transfer function and its phase is lagging, then what type of how the pole zero configuration? Lag means what?
Negative angle, sir. The pole
Negative
will
angle.
be in
Negative angle means what, sir?
denominator.
The negative angle means a pole is closer to origin, right? This
Yes,
is
sir.
the
Yes,
transfer
yes,
function like that.
yes, sir.
For leading, positive angle. Positive angle means zero will be very close and like this. If you draw the Bode plot of this, if you draw the Bode plot of this and draw the Bode plot of this, then you can know that how the Bode plot will be look like for this. First of all, a pole is there, sir. Suppose this is my transfer function or 0. Then I saw a pole means minus 20. Okay. Then I saw again a 0. So like that. Similarly, if you do this, then it will be like this. Suppose always you start from 0 to make it clear. Let's say I'm starting with 0. I saw a pole at a initially, so my first crossover function will be like this because negative slope minus 20. Then I saw a 0, so it will be like that. Okay. Now, if I go to the lead compensator, I saw a 0 first. I'm starting here. I saw a 0, so I'll get plus 20 decibel per decade. Then I'll see a pole. Then this is my transfer function. So this is the Bode plot. This is the magnitude plot. Now I'll see which one is which type of filter. Can anybody tell me? This is which type of filter? It's a high pass filter, low pass filter. Sir, high pass filter means what? And low pass filter means what? It allow low pass filter means it allow all the frequency components below the crossover frequency, right, sir?
Yes, sir. Yes.
And high pass filter means what? Which will allow all the frequency which is after the cutoff frequency, higher frequency to allow. Low pass means lower frequency to allow, right sir? This is low, this is high pass filter, right sir? Have you any idea about low pass and high pass filter, sir?
Yes, sir. Yes.
So generally, low pass filter means this is a cutoff frequency. You are allowing all the frequency component which are less than the cutoff frequency. Means all the frequency component which are above the frequency components not allowed. This is low pass filter. You saw that for a lag compensator, you get a transfer function like this. Okay, it start like this and leaks. Okay, if you now shift it, okay, and for a lead compensator, you get the plot like this. Okay, this is for a lead compensator. So, so remember that lead compensator. You see, this is a high pass filter. This is a low pass filter. Okay. So lead means you just if you want to use a shortcut, then lead में चार term है sir. चार term means it's a high. Okay. High में भी चार term. Lag में three terms. So low pass filter में three terms. Okay. So just remember like that. Lead compensator is a high pass filter. Lag compensator is a low pass filter. ओके इसमें चार टर्म है, इसमें चार वर्ड है, चार लेटर है, इसमें तीन लेटर है. इसे याद रख सकते हैं. यू कैन रिमेंबर लाइक दैट. Okay, otherwise you can do the Brody plot and see. Okay, so now if I use the combination of this, sir, lag and lead, then tell me which type of filter is this one, sir?
Yes.
Lagging.
Yeah. Yes, sir. Lagging.
Lagging, which type of filter?
Band pass, band pass.
It will be band pass filter. Okay, then similarly lead lag will be a band stop filter, but notch filter you can say. Okay, lead lag is a notch filter. Okay, okay, it's a band stop filter. Okay, so these are the basic ideas of the compensator. Now if you want to solve the question from compensator, how the compensator will be designed, okay, based on the transfer function. So first you understand that. Let me go to the controller part. Okay, this is the controller GCS. Okay, let me say that I'm just defining one transfer function by my will. Okay, it can be anything, sir. So let's say GCS is something 1 plus a TS divided by 1 plus TS. Okay, in normally compensator you have seen this type of transfer function. In another book also, if you see, this transfer function can be also like this, 1 plus TS divided by 1 plus ATS. It can be anything. It depends upon the poles and zero locations. And remember that in both the cases, your A and T, these two values, okay, should be greater than equal to 0. Why it is greater than equal to 0? If these two values will be greater than equal to 0, then all the poles and zeros should be lies on the left hand side. In control system is a low pass filter, I told you. So as a low pass filter or a minimum phase system, so all the pole and zeros should be lies in the left hand side. So whenever you're designing a compensator or controller, remember that all the poles and zeros should be light on the left hand side, because that should be a stable system. Otherwise it cannot make the error equal to 0. So these two assumptions you have to make. First, A and T should be greater than equal to 0. Then suppose I choose the upper one. Okay, this one. I'm just removing the second one. Now just tell me what is the, because lag on lead compensator is defined by the phase angle. When a phase angle is positive, it is a lead compensator. Lag compensator, phase angle is negative. So for this transfer function which is written in 1, find out the phase of that system. So what is the phase of that system, sir? What is the phase of this transfer function? Go to the first numerator, 1 plus ATS. Okay, so this is not TS, 1 plus ATS, right? This is 1 plus ST, like that. Okay, so first tell me what is the, because this is 1 plus STS, so it will be tan inverse. Okay, uh, right, omega is equal to omega t, right? So omega t into A. right? Yeah. So this is the phase of the upper term. Okay. Similarly, for the phase of the lower term, when it is coming to the numerator, it will be negative. Okay, this will be tan inverse omega t. This is the complete phase of the transfer function, right, sir? Now you are saying that suppose for a lag compensator, your phase should be negative, phi should be negative. Now in this equation 2, to make the phi negative, what happened to your a value? A value should be positive or negative? Phase has to be negative, sir. This
Yes,
term
sir.
has to be negative means this term has to be negative, right? This term negative means this a value should be less than equal to a value whenever it is less than 1, then this phase will be going to negative. So remember that for a lag compensator, if you use this type of transfer function 1 plus a ts divided by 1 plus ts, then a has to be less than 1. If in other books, if you see that this GCS sometimes written as 1 plus ts divided by 1 plus ats. Okay, if they use this type of transfer function, then for lag compensator, this a value should be greater than 1 to satisfy the equation number 2, because for this phase will be this term minus this term, reverse. For reverse case, this a value has to be greater than 1 to make the phi negative, right, sir? Are you getting my point? So I am just telling you that in one book, for they are using equation 1 as a transfer function. In other book, they are using equation 3 as a transfer function. But in both the cases, remember that either a value should be less than 1 or a value should be greater than 1 for a particular compensator, let lag compensator. It depends upon the phi value. This phi is negative for lag compensator. Now you can see equation 2, phi is negative only when a less than 1. If we use the transfer function 3, for that case, your phi will be tan inverse omega t minus tan inverse omega at. Now, for lag compensator, phi has to be negative. So, for phi has to be negative, your a value has to be greater than 1. Because this value is more, then this term will be go to negative. So, it depends upon the transfer function which you are using. Are you understanding, sir?
Yes, sir. Yes. Got it, sir.
So
Yes,
don't be
sir.
confused that when you are using a greater than 1, when you are using a less than 1, because one person can say, sir, a lag compensator a is less than 1, other person a greater than 1. So it depends upon the transfer function which you are using, how you are
Sir,
representing.
phi will be always negative for both types of transfer functions.
Not, no, sir. Why phi is be negative? For lead compensator, your phi should be positive. Why positive? Phi
Yeah,
negative?
yes, yes, no. So, yes, sir. For lag compensator, phi is always negative.
Yeah, for lag
Depending on the
compensator,
age
phi
less than
negative.
one.
Based on that, you find out your a.
Okay, sir.
Based on the transfer function, sir. Which transfer function you are using?
Yes, sir. Yes, sir. But in
Okay.
both case, phi is negative.
Yes, sir. Both the cases phi is negative because it's a lag compensator. I'm
Yeah,
explaining
yeah.
now.
Yes, yes, yes. While A is less than 1 and A is greater than 1.
Yeah, because in some books that they're saying for a particular transfer function a is positive, and for other transfer function a is negative. So just don't confuse. That's why I'm saying that don't confuse that. You just see that what transfer function they're using, and based on that, a can be positive for lag compensator, a can be greater than 1, or a can be less than 1. It depends upon the transfer function. But apply the same concept. Phi is negative.
Yes, sir. Nice, sir.
Yeah. So don't be confused, because in my earlier days I also confused because I solved the questions. I just remembered the formula, but formula will be changed. Depends upon the transfer function to transfer function. So you just carefully see that a is in the denominator or a in the numerator. So based on that you solve the question. So now if you know this concept, now one concept, one question will coming from that at which value of omega. Okay, because whenever you are using the GCS, this, let's say I'm using the first one, ats divided by 1 plus ts. Okay, this is my GCS. Now to find out what is the omega value, omega means whenever put a is equal to j omega, this is coming into frequency domain. So now for what value of omega, okay, your phi is maximum. Okay, It means maximum means what? Either the maximum phase lead, or there are two options, maximum phase lag. Now you have to find out for what value of this phi your maximum phase lag occurs, or maximum phase lead occurs. So how will you find out that? You know that maximum minima concept, sir. You know that maximum minima concept. Whenever you're finding out a maximum any value, you have to differentiate that value and make it equal to 0, right? This is the concept of maxima or minima. Whenever suppose a curve is given like that, whenever you find out this maxima point, or you have to find this minima point, you have to make a tangent. Tangent is nothing but you have to make the slope equal to 0. So this equation, whatever you have written earlier, tan inverse omega a t minus tan inverse omega t for this transfer function, okay, which transfer function I consider here. Now I want to find out that for what value phi my phase will be minimum and phase will be maximum. So at one particular omega it will be maximum, at one particular omega it will be minimum. So let me find out that value. So you have to make a tangent. Okay, find out the tangent. Tangent means nothing but slope equal to 0. So first of all you have to make the derivative, and that derivative equal to 0, that is nothing but the slope. So now find out d phi by d omega and make it equal to 0. If you make it equal to 0, then you will get a omega value. And that omega in books, it is mainly given as like that. This is given as, if you solve this equation and find out that omega value, this omega is called 1 by t. But this omega is not called a normal omega. This omega is the point at which the maximum phase occurs. So let me call it at omega m. It can be maximum phase lag or maximum phase lead. So remember this formula, okay? So this formula is same for both the type of transfer function, whether the transfer function is in this format or in the reverse format. So always this omega will be same. This omega is nothing but, we remember that if you see this transfer function, what is the zero? Zero of the transfer function is how much? This will be 1 plus a t s, make it equal to 0. Find out the location of the 0. Okay, s equal to minus 1 by a t. Okay, this is the location of the 0. Then how find out the pole location? The pole location is 1 plus ts equal to 0. So s equal to minus 1 by t. Okay, I told you that in earlier classes that this pole is nothing but the negative inverse of time constant, or time constant is nothing but the negative inverse of the pole. So now after finding out the zero location, this is the zero location, this is the pole location, now you take the geometric mean of that, these two, geometric mean of these two. Geometric mean of these two means minus 1 by 80 and minus 1 by t. Okay, these are the two, one is pole location, another is zero location. Then see minus minus get cancelled. Geometric mean means just square root of these two. Okay. So you will see that this will be coming as how much? T times of root a. Okay. So this is an omega m. This is nothing but the geometric mean of the pole and zeros. So whether the pole and zeros will be reverse, means in the pole position, means depending on the transfer function, whether the transfer function is different, so it doesn't affect this omega m. Because in other case, if you see, suppose the transfer function is reverse, GCS is 1 plus TS divided by 1 plus ATS. In this case, the pole will be something minus 1 by 80 and your 0 will be something minus 1 by t. If you take the geometric mean again, you will get the same formula, 1 by t root a. So in both the cases, whether the transfer function will be reverse or same, this omega value is same. So remember this formula. This formula is nothing but at which frequency your maximum phase occurs, or maximum phase, the maximum phase lag occur, or maximum phase lead occur. And this formula will be same for all. Are you following me?
Yes, sir.
Yeah. Uh, so so these are based on this, some formulas are there. I just uh, what is that formula? If you put this omega value, okay, because whenever you are finding out the minimum phase angle, na, You told me, sir, this is my phase equation. In that phase equation, you are differentiating it and find out at omega value. And for that particular omega value, if I put this omega value in this equation of phase, equation number 1, then I will get my phi, and that phi will be maximum because we are doing that for maximum. So it means if I put this omega value in my equation 1 of phase, then I get some phi m. This phi m is called the maximum phase lag or maximum phase lead. Okay, for a lead compensator it will be maximum phase lead, for a lag compensator it will be maximum phase lead or lag, whatever. So this phi n will be something sine inverse. If you put that omega value into that equation, you get some phi, which is nothing but a minus 1 divided by a plus 1. And you have to remember this formula also based on the transfer function. Okay. So sometimes you just see whether a is greater than 1, then you will right, because already whenever question is coming to you, you have to compare. Okay, let's say 1 plus 3s divided by 1 plus uh, 1 plus 4s is given. Suppose whatever the transfer function you like, I don't know. Let's say GCS is this one. Suppose you like the first transfer function. Compare with the 1 plus ATS divided by 1 plus TS. Okay, you compare. Someone is comparing with this transfer function, then he will get some A value, whether that A value is less than 1 or greater than 1, and for that he decides that whether it is a lag compensator or lead compensator. Other person doesn't like this formula transfer function, he choose 1 plus TS divided by 1 plus ATS, then for him A will be different. Then you just see whether A is greater than 1 or A is less than 1. For you, I am just telling you how you solve the question. You find out A value, you just see that for this transfer function whatever you choose, you get some A value greater than 1. Then in the question he is asking us to find out the phase at which maximum phase occurs. So whenever A is greater than 1 means you have to use this formula. Suppose one person is getting A less than 1, then he used the formula just is like this, sine inverse 1 minus A divided by 1 plus A. Okay, because in this case A is less than 1. So for A greater than 1 you choose this formula, for A less than 1 you just reverse that. Okay, because I don't want my numerator to be negative, I numerator to be positive because this is a maximum phase. So like that you choose. Okay, so don't be always use stick to this formula, a minus 1 divided by a plus 1. It can be 1 minus a divided by 1 plus a. It depends upon what a value you are having. If a is greater than 1, then use this formula. If a is less than 1, then use this formula. Because this omega m is same for both. Okay, it cannot be changed. So for this, whatever a and t value you are getting, find out that omega m. But for phi m, whenever calculating phi m, you have to check in your hand either a greater than 1 or a less than 1. If a is greater than 1, then use this formula. Is less than 1, then use this formula. Are you understanding what I'm saying?
Yes, sir. Right.
Okay. So, so let me give one question to you. Okay. Yes, one question will solve and everything will, the doubt will be cleared. Okay. Let me give in the transfer function. Let me give you the transfer function to you. Sometimes the transfer function is not given to you. Let me give an example for that. Let me give the transfer function like C and R and R. It is given like that. This is given C1, this is R1, some value will be given for that. This is given R2. So this transfer function is non-known to you. This is the output V naught, this is the input V in. You have to find out your transfer function part. V output divided by V in. Just apply the what is that? You have to just apply voltage divider rule. Okay, R2 divided by, let's say this one is, this whole transfer function impedance is Z1, so R2 divided by R2 plus Z1. Okay, you solve and you find out the transfer function. I am just giving that transfer function. After you solve all this, the transfer function I am giving, let that transfer function will be k into 1 plus 0.3s divided by 1 plus 0.17s. Okay. Now for that he is asking us to find out what is omega m and what is your phi m. So if we use the formula like this, 1 plus ats divided by 1 plus ats divided by 1 plus ts, then if you compare, you find out your at is nothing but 0.3 and your t is nothing but 0.17, right? If you put this t value here, then what is the a value? 0.3 divided by 0.17.
Sir,
Whether
what about K, sir?
k is a constant, sir. K is nothing but nothing is given to you. Just k, actually what is k na, sir? Whenever you solve this na, whenever you solve this value, c1 is something, r1 is something, r2 is something, then you will get a coefficient here k. That coefficient is that k. Just I am denoting that is a k is a constant. Let's say it can be 8, it can be 3, whatever. But for that, now what you do, you just actually in compensator design, whatever this k value is there, we are multiplying one extra factor, the gain at the output of the compensator, to nullify that value. Because always what you do in your transfer function, this is always in this format, 1 plus ats divided by 1 plus ts. Let's say this k value is a 10, then if you multiply this 10, then this transfer function is now 10 plus 3s divided by 1 plus 0.17s. But it does not follow our standard equation. Our standard equation is always in the format of 1 plus ats. So to make this 1 plus ats, whatever the common term is there, you just take it common. So in this case, let's assume that I have taken the 10 common to make a standard equation. So that value, 10 value, you have to, after the compensator design, you have to choose a gain of 1 by 10 to cancel that value. Are you getting my point, sir?
Yes, sir.
Yeah. So this k value is like that. This k value I have chosen in such a way that to make my transfer function, which is identical to the transfer function which I am going to solve the problem. So my transfer function is like this, 1 plus ats divided by 1 plus ts. So to make 1 plus something, I have taken the k common, and whatever the k is there, after my compensator, I have designed the proper value of a and ts. This k value has to be cancelled. After the compensator output, you have to put one gain. That gain equal to 1 by k. That 1 by k and this k get cancelled. Right, sir? So now after this, you have to choose your at value and t value and find out the a value. 3 divided by 17. So this value is less than 1. If a is less than 1, then you know that this is which type of compensator is this one. A is less than 1 plus ats divided by 1 plus ts. A is less than 1. So which compensator is this one? Lag compensator, I think. Because phase is what? See, A is less than 1. A is less than 1 means it's a lag compensator. So this is a lag compensator. Okay. So for the lag compensator, you have to find out at what value of omega your phase maximum phase lag will occur. So this phi m is nothing but phi m for phase lag, because this is a lag compensator. So find out omega. Omega is nothing but by this formula. Okay. What is this formula? 1 by t root a. 1 by t root a. Next, phi. Phi m is what? Sine inverse a is less than 1. So I put the formula like this, 1 minus a divided by 1 plus a. Are you getting my point, sir?
Yes, sir.
Sir,
So,
but here a value is more than 1, sir.
no, sir,
0.3 by 0.17.
3 divided by 1.7, right? So,
Point 0.3, sir. Point
ah,
0.3 it is.
I'm sorry. So its value
Mhm.
should be greater than 1. If it is
Yes.
greater than 1, this is the lead compensator. If this is
Yes.
the lead compensator, then this formula will be a
1
minus
plus.
1
A minus 1 by
divided by a plus 1.
A plus.
Okay, so like that, sir, you have to solve that question. This is nothing hard and fast on compensator controllers. These are very easy things to implement because it's just the addition of another transfer function into your original planned transfer function, and the same property will be valid because now your transfer function is not only planned transfer function. Your transfer function is the combination, cascade combination of your compensator, controller, and your main transfer function. Now make that three combine, and whatever the question you can solve, whether it is steady state error, whether it is a root locus, whether it is a Bode plot, whatever. So you solve that question. So I stop here. So next class onwards, I think sir, most the design part will start. Okay. So in the design part, maybe some MATLAB related things will come. So we'll see how to solve that. So you solve any question. If in doubt, you can text me if you're not solving. So no problem. I'm just closing the class today here. Thank you all of you.
Thank you, sir. Thank you and good night, sir.
Good night, sir.
Thank you, sir.
Thank you so much, ma'am.